Hello everyone, good morning. So welcome to the second episode of our YouTube live on applied mathematics. So today we're going to talk about something truly interesting, okay? That's the Green Theorem. So it's Green Theorem, and it's not green, sorry about that. And George Green is also a very interesting mathematician. He I believe, only attended formal schools for about 1 year. And so then he come up with lots of interesting mathematical theorems and also cook up the idea, basically developed the whole idea about the potential theories in electromagnetism. And so I believe since George Green just learn all the tricks and the techniques and write down the books. Well, back in 1828, that was almost 200 years ago. And I hope with a little help of this short videos, you can then pick up these materials without any problems. To make the long story short, what we are going to talk about is a very cute, what we call the bulk boundary correspondence in calculus. That is, taking a domain like this in this area, so then it has its boundaries. And it's rather surprising. The bulk integrals like this one can be changed into the boundary integrals. Okay. And I can assure you that this sort of bulk boundary correspondence happens all the time. In fact, when you take the basic calculus, you already learned the concept. You probably just didn't think about it this way. Okay? And so before we start, let me just remind you one more time that learning applied mathematics from YouTube Live is certainly not the same as attending physical lectures. And as you know, that the pandemic situation is a little bit chaotic at this point. So I do hope that every one of you can take good care of yourself and try to stay safe. And hope your immune system is strong enough to defend the viruses even when you got infected. And coming back to the applied mathematics, so if you have followed the videos, you probably know it's a little bit surprising that now Google has really smart algorithm to translate my poor English into closed captions. And I double checked with the closed caption. It seems to work properly fine. It's probably not perfect, but for those of you, if you find listening to English a difficult challenge for you, then you might turn on the closed caption so you at least have some cues about what I'm talking about. But most of all, learning these mathematical tricks is really not just listen to this short video. So let me emphasize one more time. Okay, so this is the textbooks. So please read the textbook. In particular, please do finish the exercise on yourself. I probably repeat myself many times like this, but this is really the way that you finally get familiar with this one. And for those of you who is not satisfied with just this book, you can either ask your additional questions in eLearn, or you can interact with me or TAs. Okay? So don't worry, we have multi-channel to communicate with each other. Okay, dokey. I hope that would be enough warm up. So let's go back to our learning materials. So let's look slightly deeper into the Green Theorems, and you find it really cute. This whole idea is that you have two functions, p and q. And somehow you do this p dx and q dy along this contour. This contour, because this contour, this closed contour, is a boundary of an area A. So then I write it as partial A to denote their connections. So A denote the green area, okay? And the partial A then denote this closed contour. And typically we use the right-hand rule, so it's a counterclockwise. And if you just do p dx, q dy integration over the closed contour, then you get this integral. Surprisingly, if you then take partial derivative of q with respect to x, so you get dq dx minus dp dy. And these combination as the integrand in the bulk integrals dx dy for this entire area, you find these two expressions are identical to each other. How can this be true? How can a bulk integral equal to a boundary integral? If you exaggerate a little bit, this is almost like you can judge a book by its cover, right? So instead of reading the book, you just read the cover and then you know everything. How can this ever be true? If that is true, then you just go back, grab your applied mathematics textbook and carefully study the cover of Riley, and then you know all material inside. Is that what it means? And of course, for those creative minds, you might think, aha, I know how this works. This is partial q partial x. And if I just cancel this partial x with dx here, I got a q dy. That seems to be these terms. On the other hand, if I then cancel the dy with the dy here, then I got a partial derivative, p dx. Well, nice try. And so there's some flavors of being correct here, but of course it's not, right? If that argument works, then where does this minus sign come from? So today I'm going to march you through how you can understand Green Theorem properly, and we will provide a kindergarten level proof of it. But most of all, there are quite some examples and exercise. Please walk them through, making sure you understand this bulk boundary correspondence. And once you understand Green Theorems, you can apply Green Theorems and develop what we call a potential theory. So a potential theory is trying to use a scalar field to describe a higher level the vector field. Okay, so most of the time, vector field has three components, scalar field have only one component, so there's no reason why this works. So there are some criterions, and once you learn the Green Theorems, it's very easy to move forward. So let's wait and see. Okay, so first of all, I'm going to start with the proof. Sorry to really start your beautiful morning this way. Okay, so rewriting the Green Theorem, the left-hand side is what we call a contour integral. So it's an integration along the curve here. It's p dx and q dy. On the right-hand side, that's dq dx minus dp dy dx dy. So it's an area integral. So what I'm going to proceed is that I'm going to turn these terms back into the contour integral and see what happens. So to make this happen, one of the most convenient ways is really trying to write down the double integrals carefully. So details are important here. So looking at the contour here, okay, when you perform the areas, naively we can say, oh, we just cut it into little pieces and then we calculate it. Conceptually, this is right. This is absolutely right. Nothing wrong with that. But in reality, that's not what we really perform the integrals. So here I'm going to, for instance, if I want to compute the double integral on minus dp dy, what I'm going to do? Well, I'm going to cut the contours into two parts, the upper part and the lower part. So then I have two functions, y2x and y1x, as highlighted in color of blue and green. And then I'm going to integrate the x. And so for each x, you are really just running from y1 to y2. So let me draw this one more time. Suppose now if you integrate this whole thing, so now if you integrate for a particular x, you will basically integrate y1 to y2 like this one, right? And so you can change your x. So you just move from here to here, and then you move from here to here. And if you just run through all the integrals, then you run through the whole entire area. So let's see how this works. So let's show the algebra here. The idea is that we want to compute this. So that's d1 dp dy. And then I shuffle, okay, the order of the integration here because I want to carry out dy first. And as I explained, when you do that, you need to specify the boundaries, the upper and the lower and upper bounds. So for it to go through this whole areas, this x go from A to B. So that's why this is A and this is B. So there's no problem. For specific x, this y go from non-trivial value to another non-trivial value, and this non-trivial value is defined as this y1 function, and the upper bound is defined as the y2 function. So for a chosen x, you just perform the integration from y1 to y2. Pretty nice, right? Okay. So then here we are safe with the algebra. So you're just facing this integration, but this integration is somehow trivial because it's partial p, partial y, integrate over dy, and we know how to do that. It's basically just p. And then plug it into y equal to y1x and y equal to y2x. And once you plug it in, so then you got one term here, you got another term here, watch out for the minus sign. And I will reshuffle the lower and upper limits so then to make the sign correct. So there will be one term here that just give you minus from A to B and P integrated over y1x. And there will be another term that is A to B. Oh, sorry, here I reshuffle it, so it's B to A, and then it's P y2x. Okay, so let's look at what does this mean. What this means is that you integrate over dx, but then along a specific path, right? That path is x coordinate is x, the y coordinate is y1x. What does that mean? Well, that just means that you're integrating over this, right? A to B. On the other hand, when you are integrating this, what does this mean? This means that integrating dx from B to A. But what are the coordinates? The coordinates are x and y to x. So again, looking at the figures, going from B to A, following the trajectories of y to x. So that is the upper part. So you found this very interesting thing that the first term is integrating on this part. The second term is integrating on this part. And of course, if you add it all up, that's just the integrations around the contour. So this contours in the textbook is written with the notation C, and here I just highlighted that this contour, this closed contour C, is nothing but the boundary of the area A. And the boundary of area A is, we just adapt this specific notation, that's partial A. So that denotes the boundary of the area A. So that said, we finally got this first interesting result. That is, this area integral can now be turned into this circulations. That is, this PDX along the contour integral. So that's half of the theorem. What about the other half? Well, okay. So I have showed you how you can turn these terms into these terms. So not surprisingly, right now you probably know our remaining job is to change this dq dx into the q dy terms. And so here I'm going to use a less familiar ways of decompose the contour. Typically, when we plot the functions, we are more familiar with the expression that y1, y2 as a function of x. But here we are going to cut the contour, okay, cut the contour like this one. So then this closed contour becomes two functions, x1y and x2y. So you probably need to rotate your heads 90 degrees to make sure that, oh, indeed, you get an x2 and you get an x1. Okay? So once you have known that, everything is simple. And you probably know that what we are going to do. What we are going to do is that we are going to run the y's from C to D. And for each specific y, you know that this x is coming from x2s to x1s. Okay? So let's see how you... Oh, great. I think I marked this whole thing incorrectly. So let me change it. Dun, dun, dun. So this should be x1 according to... I have introduced that, but then I know what I have written before. It's just a notational difference. Okay, so it's x1 and x2. So let's keep these figures and see how we can massage our double integrals a little bit. Okay, so this is the double integral we're interested in. But as I said, the details are important here when you perform multiple integral together. So writing down the upper and the lower and the upper limits of the dy integral, that's going from C to D, so that is this part. And how do you do this dx integral? Well, for a fixed y, this x goes from x1y to x2y, x1y to x2y, and then this is the original integral. Okay, once you get this important point, then this integration is something trivial. You can just carry out this partial integration, and then you get qxy with now not y but x plugging into x1y and x plugging into x2y. So for the x1y, it has a minus sign, so then we can absorb that minus sign by changing the lower and upper bound from D to C. On the other hand, for this x plugging into x2y, it's simply just C to D. So now you got these two terms, and let's see how this step means, what that means. Okay, so for instance, for the C to D, and then this x2 as a function of y, like this one, that means you're integrating from C to D, but the xy coordinate follow this curve here. And this is treating as x2, y, and y, right? So that's the definition of the contour. On the other hand, you have integrations from d to c, but now it's following x1. So you're from d to c, but then following the specific x1 and y relation. So that's basically following this contour. So if you add both together, then you got a counterclockwise contour integral. And that is what we want, right? So then you got this term here. And so let's review a little bit. From the previous one, we proved the partial derivative of p after double integrations can be reduced into this circulation integral with a minus sign. On the other hand, for another term, the partial derivative of q inside the double integrals after basically the sum calculation lead to the circulation of q with respect to dy. So now you combine them both together, and then you got this very beautiful Green theorems. Okay, here I don't need to highlight this anymore. Okay, so this is something really cute and really nice. So please look at this whole picture one more time. So on the left, sorry, just erase my notes. On the left hand side, it's a contour integral. That's what I mean. What I write here, it's a boundary. It's about the boundaries, right? The value of these contour integrals only occur on the boundary. If you really evaluate all these terms, the integrand, the value of the integrand only happen on the boundaries. It doesn't matter what are the values of p, xy, and qxy at any other position other than on the contour C. On the other hand, if you take dq dx minus dp dy and performing the area integral, that's a bulk integral. You need to evaluate these values all over or inside the area and then perform the integration. So it seems that this contains more information, right? Where this contains less information. But somehow they equal to each other. That means that the information content is equivalent. That's truly deep, isn't it? This Green Theorem is basically a rigorous proof telling you if you know the hidden structure in a book, you can judge a book by its cover because the information content in its cover is exactly the same as that content inside the book. Okay, that said, you might be totally surprised, but don't be that surprised. That is really because the integrands has specific relation with each other. That's what we call that these are not independent informations. They are hidden structures. Okay, and this in data science happens all the time. So most of the time we care about many important parameters in the data, then forget most of the time for the data that we are interested in has very specific formats. They are just not random distributions in all possible combinations. So here I'm going to show you a brief notes. Okay, this brief notes is the fundamental theorems in simple calculus. Okay, so what is the fundamental theorem? The fundamental theorem tells you that if you have a capital F, the df dx is just a small f. So if you take an integration from x1 to x2, it then equal to fx2 minus fx1. So if you forget about this, please go back to your calculus lectures and you will find it. Then you realize Green Theorems bears the same signatures as you learned this before. You just need to really open up your eyes. So this is a book, right? This is the whole segments. You calculate the whole segments and got the integrals. But then the segment has a trivial boundary. It's 2 points. So then this whole integram, okay, this whole integram going through every single point and then performing the integral actually equals to the boundary summations. Well, the boundary has the directions. Okay, they're pointing out. So this is pointing in the right. The x2 is pointing in the right, so that's positive. The x1 is pointing in the left, so that's minus. So then you got this one. So instead of just using algebraic understandings, if you really try to sort of put the fundamental theorems of basic calculus on the one-dimensional space, the geometry interpretations still tell you the same spirit. That is, you have a bulk integral which can then turn into a boundary integral, but because the boundary now is trivial, so that integral basically just turn into a directional sum of 2 points. And so you can see Green theorems to some extent can be understood as a two-dimensional generalization of the one-dimensional version known as the fundamental theorem of calculus. And if you can follow the logic to this point, you might then ask, if one can generalize a fundamental theorem of calculus from 1 dimension to 2 dimension and get the Green theorems, is it possible that we can also generalize Green theorem to 3 dimensions? And if you have this question in mind, then yes. So your brain is awakening. In fact, we can take in a curve perspective and rethink about this whole thing. So we can actually introduce a 3-dimensional vector field. A special case is x component is p, is y component is q. Okay, so this p is a pxy and does not carry any z dependence, and then this q is qxy and it does not carry any z dependence. And as we learned, for this vector field, we can calculate another vector field. That's the curl of the field. And so we're writing down ijk, dx, dy, dz, and pq0. And so then you can calculate that one by one. For the x component, okay, you get minus dq dz. But since q is a function of xy, so that's 0. So that is the first 0 we get. For j, then you got this term, so you got dp dz and dp dz, since p is a function of xy, so that is also 0, so that's the second 0. And for the k, the z directions, then you got dq dx minus dp dy, so you got dq dx minus dp dy. Aha, you see there's very cute things. For the curve v, you got a component which seems to occur on the right-hand side of the Green's theorem. For the v, the vectors p and q, that seems to correlate it to the boundary integrals on the left-hand side. And that's indeed correct, right? You can actually write v dr, and since the third component is 0, so it just simplifies to the form of p dq. Well, p dx and q dy. So indeed, the left-hand side can be written this way. And don't forget, area can be treated as a vector. So dx dy has a direction in the z direction. So thus, the double integral of the surface integral can really be turned into the vector form. And that, I changed my notes again. and that is the curl v dot ds. So this ds is dx dy along the ek direction. Okay, and so then it seems now I can rewrite the Green Theorems in terms of everything I have learned before, right? These are the line integral, surface integral, vector fields, and the curl of the vector field. So nice. And since once you write it this way, it's tempting to assume that this might also work in 3 dimensions. And in fact, it does. And it has a very famous name. This is what we call the Stokes theorems. So now you sort of make the connections. If you're starting just from the 3-dimensional Stokes theorems and take a very special case that its z component is 0 and its x and y component only depends on x and y coordinates but not on the z coordinate, then you get the Green's theorem. So I do hope later on in following lectures, we will, of course, we have some short videos explaining what Stokes theorem is and how you can apply it. So I won't say too much at this point. I just want you to know that there is a connection. That is, the Green theorem seems to be a generalization in 1D that's known as fundamental theorems of calculus. And thus, there should be a 3-dimensional version of the theorem. And it does. Okay, so I hope so far so good. Let me just check how you guys are doing at this point. Okay. So we got some people here. So is there any questions about the materials so far? I will wait for your response a little bit. Am I just talking to the air? Possibly. Scary. Okay. So if you have any questions, you can you can type in the chat room, so I will see, and then I will take appropriate timing and answer your questions in real time. And if you just tend to watch the replays, what exactly are the function P and Q? That's a really good and interesting questions. Can you explain why Green theorem can be written in blue one? In blue one? Oh. Okay. So what exactly is P and Q? So the beautiful part of Green theorem is that there's almost no constraints on what P and Q can be. So that's why it's very powerful. So Green theorem is not about a specific function P, xy, and Q, xy, so then it has this. No, it works. It works for general P, xy, and Q, xy, as long as their first derivative exists and continuous. So this is something truly amazing. And also, I guess you probably, He同学 is probably asking that why Green's theorems can be written in the blue one. I guess it's this one here. So I'm just saying that taking this vector form, calculating this vector form, okay, I can recap the Green theorems into this form, right? V dot dr has 3 components, but since the third component is 0, so then everything turns out to be 0. Curl cross V's only have 1 component, that is this one, and dotted with ds along the z direction, then you get back to just this expression. So then they are the same. And this is, of course, not a proof. It's just an explanation saying that there's a very beautiful way of rewriting Green theorems. And this expression does not seem to depend on any specific coordinate, and thus one can guess maybe it also works because it does not depend on any coordinate. So you might think because this inner product is also defined, well defined in 3Ds, and all these quantity are always well defined in 3 dimensions. So one can just guess that maybe there is a theorem of this sort in 3 dimensions. And that guess turns out to be correct. Okay? I haven't got calculation 3 yet, but I'm getting there. Good. Excellent. Great. So thanks for the feedback. So then I know that I'm at least talking to some Homo sapiens during the YouTube live. It's always great to have some feedback. So then we are going to move on to the second subject. The second subject is important in physics. That is what we call a conservative field. And there is a sidetrack joke where I was leading a team to rewrite the high school textbooks. And I got a proposal. So I indeed write a short proposal to the Ministry of Education. Because the conservative field, the conservative force, is translated incorrectly in current high school textbook. I believe in the textbook, a conservative force is translated in Mandarin as 保守力。可是这个真的是很好笑的事情啊，就是 yes。在政治上 there are conservative and liberal 保守跟自由这样，所以有保守力，那所以是有自由力咯，所以现在力是在做政党的竞争嘛，好，所以静电力是保守力，那所以自由派就是不受控的此力嘛。我每一次就想到这觉得很好笑，所以我就想提议把它改过来。其实在你们高中的时候学到的保守力，它的正确翻译其实应该是守恒力。守恒力的意思就是说，这个力最后会让某一些量守恒。那我们当然都知道，因为一个守恒力其实背后就会有一个什么，就会有个位能。那如果你把位能跟动能加在一起，它们是守恒的，所以它其实就是守恒力啊。好，我们并没有把能量守恒定律翻译成能量保守定律，所以不知道为什么在这里就歪掉了。那我写了 proposal， 然后也试着争辩了1、2次，但最后其实还是没有改。没有改的原因，我自己是觉得还蛮好玩的。没有改的原因是说，保守力都教这么久了，好像也没有造成严重的大脑伤害，没有吗？我不确定哦。所以我们就继续这样教下去吧。Okay, so that is a slight fun trivia for you about the conservative fields that I encountered when writing high school textbooks. So let's go back. The concept of conservative field is relatively simple. There are many ways that you can define a conservative field. Here, I'm going to just use a very simple geometric method. That is, what do we call a conservative field? That is, if you find the contour integral along any closed contour like this is 0, okay? Then we call it conservative fields. And please, sorry, I just triggered my theory. And please be careful about the criterion here. It means arbitrary contour C. If you just find a specific contour, you calculate the contour integral and you find 0. Well, that's not surprising. Okay. And in physics, For this particular type of integration, we have a name. Okay, it's called circulation. So please keep that in mind. If you're trying to calculate something like this, sometimes we will just say that if a field is circulation is always 0, then it's conservative. So the circulation is just a shorthand notation of saying the integrations over a closed contour. Okay, so the figure is like that. But this criterion can actually be changed into another form. So let's just do that. In particular, I found that the copy and paste functions on iPad is really great for teaching. So you can actually cut this contour into 2 parts. Okay, so that's a C1 and a C2, and reverse this whole thing. And so then this closed contour will then become basically the integration over C1 minus integration over C2. And that is always 0. So what does that mean? That just means that for a conservative field, if you have an open contour with 2 endpoints, as long as the endpoints are the same, the integration over one contour would automatically equals to the integration over another contour, like this one. And because this integrations only depends on the endpoints, as I show here, right? And so then we can define a potential function, which of course only depends on which location you are, and then the difference between them. And the asterisk minus sign here does not appear in the mathematical textbook. It's just for physicists and chemists that we tend to say that the system was settled in the lowest energy. And if you like that concept and terminology, there is a minus sign that you define here. Okay, so you can change this minus sign, but then you will be basically against all physics textbooks. So I would advise you not to do so. And so, but don't be scared by this minus sign. It's just redefine your potentials, flipping it from what? You just flip signs. So in computer science, sometimes we also do that too. So that does not have any fundamental reasoning behind this. The key point is that for an arbitrary closed contour, it can be cut into 2 contours with the same endpoints. And in fact, if you think about that, this also works reversely. If you have 2 contours, and if you just reverse, for instance, C2, then you just got a closed contour. That's the same thing. Okay? So it's the same to say when do you have a conservative field. That can be said as that for arbitrary contour C, its circulation is always 0. Or you can say for any open contour with the same endpoints, their contour integrals give the same result. They are the same statements. And once you have these relations, we can further develop what we call the potential theory to really elucidate the connection between the vector field and the scalar field. So let's see how that goes. So the notion of potential is the following. First of all, trying to try out all contour and calculate circulation is 0. Of course, it's time consuming and it has logical bug because you cannot perform infinite contour. So it's better that we apply the Green Theorem, and that's why it is so important. Applying the Green Theorem, if this is correct, then we can use the Green Theorem, transform the contour integral into this area integral. And this area integral is 0 for arbitrary contour, which means the arbitrary area And so that can only be true by the criterion of the integrand itself vanishes. And the integrand is just dfy dx equal to dfx dy. Okay. And so this is a much easier criterion. And since it is really straightforward, so I will just leave you for detailed calculation, and I won't give you examples in this short video here. But this is basically the key result that we get out from Green Theorem. Think about this. Geometrically, we can either define a conservative field by circulations over arbitrary contour, or we can also define by basically the integration, or you can say the work done by the conservative field only depends on the endpoints. Both are equivalent expressions. But these expressions, these integral expressions are conceptually useful, but not very useful in terms of real calculation. If I just give you some fields, how are you going to know it's conservative or not, right? And so these are the truly useful criterion. Because you write down fx, you write down f of y, you just take the partial derivatives and to check whether they equal to each other. And if they do, then yes, you got a conservative field. How nice is that? And so sometimes when the question asking a contour integral, which is very annoying, very hard to calculate. And if it's a conservative field, then you can change it into a much simpler contour and perform the result. Okay? So that's a notion of potential. And so finally, we are going to show you how you can construct the potential phi r. As I said, so if you're rewriting the previous definition, we can say a potential at an arbitrary point and subtract by the potential energy at the origin is nothing but a contour going from 0 to r and then just calculating the integration. Okay, I'm just reshuffle the term here. So it's relatively simple. And you also know that the potential is always defined up to an arbitrary constant. That you cannot really pin down the potential energy is just this particular value. No, it's always legal that you can add some constant to the potential energy and it still works. So that's the integral form, that how you can get the gradients. But once you got this one, and if you compare with the definition of gradient, then you find out that, wow, the new concept, the new trick is the gradient that we learn is going to be really useful here. Why? Well, starting from the total differential d phi. D phi can be written as gradient phi dot dr, right? That's the differential form. And if you just integrate on both sides, so integrate over d phi just give you delta phi. So that's the phi difference as at 0 and r. And the integration over this is nothing but this. So then compare this expression here. This is delta phi equal to gradient phi dot dr, integrate over some contour. This is a vector field f, integrate over dr with a minus sign, equal to delta phi again. Wow. So by comparisons, you immediately got this very interesting result relating that once you got the potential, how can you get the field? Well, just taking the partial derivatives. So these two are dual relation between a potential and a conservative field. A conservative field is a it contains three components, right? In 3 dimensions, and in 2 dimensions it contains 2. So in principle, it should be more informative. But as long as it satisfies the criterion that its curl is 0, it can be described by a scalar field. This is a great simplification, so try to keep that in mind. And so this is of course not free. So not every field has a corresponding potential. Please do not take me wrong. Only those fields satisfies these criterion or equivalently this criterion will then has the corresponding potential. Okay, so let's try to see some real examples. So these are the typical example, the good guys and the bad guys. So let's try to see what happens. Suppose now I have a really long and straight wire in this, and I'm looking down on the XY plane. For electric field, I have calculated for you that this electric field is lambda divided by 2 pi epsilon naught rho. Rho is the distance here, and E rho, that's in the radial direction. So we're using cylindrical coordinate because the symmetry is here. So the E field can be written this way. Okay, taking pretty much the same geometric setup, okay, a very long straight wire, but now passing currents instead of carrying charge density on that. And if you're passing some current through the wire, it will create the magnetic field around the wire, right? And use your right hand. And if you write it down, then you got a B field here. The B field after calculation by Ampere's law is mu 0 I divided by 2 pi rho in the E phi direction. Okay. So how are we going to know that the electric field and the B field are conservative field or not? Well, simple. For E field, for instance, for demonstration, I can take this circle, right? And because all E fields are perpendicular to this one, so it is zeros. And turns out, this is suggestive, okay? This is not a proof that it is conservative. It is suggestive that maybe it's conservative. I will show you that it is indeed conservative. On the other hand, if you just do this whole thing, you choose the circle and you perform the integration, the BDR, and you will find circulation is nothing but mu 0 r, because it's mu 0 I 2 pi rho times 2 pi rho. So the 2 pi rho cancel out and you got mu 0 I. And this is not surprising. This, in fact, is the integral form of Ampere's law without Maxwell corrections. So it is right. And since I have already found a contour, which then lead to non-zero, non-vanishing circulation, so I know for sure that B field is non-conservative. Okay, so the logic should be straightforward because it should satisfy for all contour. But I found one contour that its value is not zero. So I have proved that the B field is non-conservative. But for E field, it's suggesting maybe it's conservative. So how can we make sure the electric field is indeed conservative? Well, by the trick that I have learned, well, I have showed you, that is just compute its curve. Because the criterions that we showed before is nothing but asking its curl is zero. So we have this electric field, and I do hope that you have catch up because I told you guys how to calculate curves, okay, in general curvilinear coordinate. If you forget, let me give you a 5-minute reviews. These are the previous slide that I showed in the classroom. That's the summary, right? So here, this is the gradients, this is the divergence, this is the curve, this is the Laplacian. And in curvilinear coordinates, because for the cylindrical, spherical, Cartesian coordinate, all the base vectors are orthogonal to each other. So it turns out that the complication can be embedded by 3 scaling functions, h rho, h phi, and hz. And for cylindrical coordinate, it's relatively simple. This h rho is 1, the hz is also 1, and the h phi is rho. So if you really try to calculate, for instance, the curl, then you should put products of h1, h2, h3 outside, and then you arrange your base vectors this way, and then arrange your components this way. Okay, so I hope that revive your memories about the vector operators in curvilinear coordinates. And so let's go back and see what happens here. Dun, 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 dun. Is this the right page? Yes, this is the right page. So multiply them to get all together, right? So then you got 1 times rho times 1. So that's 1 over rho. That's great. And this is 1, skip that. Rho here, 1 here. Excellent. The second row is just partial derivatives with respect to the variables. So it's dd rho, dd phi, dd z. Also easy. The third row is h times the correspondence vector component. But since it only got the e row component, so you only got e row here, and all others are 0. So let's try to compute the curves term by term. First one, computed along the row direction. This should be trivial. That's 0. And calculating that along the phi direction, this term is 0. This term, well, is dE rho dz. But then looking at this E rho component here, it does not carry any z component, z dependence. So that is 0. Yes, so the second term is also 0. The third term is this, crossing this out. This is 0 minus this one. So we encounter the dE rho d phi. But again, because this E rho here only depends on rho, it does not depend on phi. So the partial derivatives is still 0. So then it's still 0. So it's 0, 0, 0. Yes. So its curve is completely 0. That means the electric field is a conservative field. Yes. So that justify our guess before. In fact, for curious cat, you can convince yourself you can construct the corresponding electric potential, which I won't bug you. That takes a very simple form. That's basically just minus sign, the annoying minus sign. Lambda divided by 2 pi epsilon naught. Lambda divided by 2 pi epsilon naught. And log rho. So if you then take this phi e's and use the gradient formulas that we learned in curvilinear coordinates, okay, try to calculate the gradient of the electric potential. You will get the correct form of the electric field. So it's perfect. And I do hope that this straightforward example sort of give you some concept that how you can really combine the vector field and the scalar field together and try to get familiar with all the relationship between them. So there are quite a lot of different perspectives that you can talk about. And you might think that I'm going to end my lecture today, and yes, we are coming to an end. But I have a big puzzle for you guys. Okay? Since this is YouTube Live, there's always a way that you can look back. Finally, I can be slightly more freestyle than I teach in the classroom. Well, in fact, I enjoy teaching the YouTube Live better, much better than teaching in the classrooms. And so I'm going to show you something really mind-boggling. Remember that I choose a contour and showed you that the B field is non-conservative, right? So the logic is correct. Even though the calculation is trivial, it's actually mathematically rigorous. Okay, that was a proof. So we just proved that a magnetic field created by a long straight wire is non-conservative. Here I'm going to show you a slightly different ways. Okay, even though that calculation is simple and straightforward, maybe you just want to try out the curl calculations. Why not? Let's do that. Okay, let's do that. So what is the B field? Well, the B field is cute. The B field is mu I divided by 2 pi rho, but now it's in E phi direction. So, and by now, you should be able to write down the curl formulas in cylindrical coordinate as in the electric field. In fact, you just copy that calculation here. You get 1 over rho, and the base vector has 1 rho 1, okay? And the second row is just the partial derivatives with respect to rho, phi, and z. And the third row, you just write down the magnetic components of the B field. And you only got non-zero E phi component. So this phi component, be slightly careful, must be multiplied by rho in our formula. And once you multiply rho with B phi, what did you get? You get something relatively simple. You just got mu 0 I divided by 2 pi, which is a constant. What does that mean? Well, that means this is 0 constant 0. Yes, a constant is not 0, but then you know you're going to be acting upon all the derivatives. So I don't need to go through the detail, all the derivatives. After you do that, it's going to be 0 because you're taking derivatives of 0 or a constant. And then just sum them up with plus or minus 1. It's going to be 0, okay? It's going to be 0. So it's 0, 0, 0. No, this is disaster. Disaster number 1. The curl B vanishes. How can that be? If you were not smart enough to cook up the loop around this whole thing, you just jump into, or you brainwashed by Professor Hedgehog saying that, well, you know, don't try out to count to us. Most of the time, this approach doesn't give you any definite answer, right? So you just calculate the curl, and you calculate curl. It is 0. You run into the incorrect conclusion that the B field is conservative. Or maybe B field is really conservative, that your high school teachers are just not courageous enough to teach you so. So, let's move on. Things get worse. In fact, I can construct the magnetic potential phi B. Yes. So don't ask me why. Suppose now that I'm being smart enough. So I'm writing down phi B, just a scalar, no component, right? It's minus mu 0 I divided by 2 pi. Well, it's a must because you got that component. And an angle phi with a minus sign. And right now, let's calculate the gradient phi B. So writing it down is d phi B d rho, d phi B d phi, d phi B d z, with the correction that 1 over 1, 1 over rho, and 1 over 1. Okay, so I'm writing it down explicitly. And as you can see here, this phi B does not depend on rho, or does not depend on z. So then d phi B d0 is 0, d phi B dz is also 0. And what about this term here? d phi B d phi, d phi B d phi, sorry for the bad notation. You just cancel this out, you then just got minus mu 0 I 2 pi and 1 over 0. You got this one. Yes, this is just really minus B, right? So you can see that, in fact, the magnetic field can be derived from the magnetic potential. Wow. Wow. So the magnetic potential exists. So I have showed you that the curl B is 0, okay? So it's confusion number 1, which seems to indicate the B field is conservative. And being a curious cat, you can ask forward, right? If B is conservative, then there should be something called magnetic potential, right? And taking gradients, and then you can get back the B field. And in fact, I can construct the magnetic potential. And then you indeed got this. Wow. Why didn't you learn this in high school or general physics? Are your professors and high school teachers trying to hide something from you? That is the big puzzle that I will try to pass on to all of you, which means that I'm not going to tell you the answer by being teacher. And the second thing, as a bonus, okay, in addition to these big puzzles, for those curious cats, I certainly encourage you, if you try to calculate the ratios of the magnitude of the electric field and the B field, you in fact find something pretty cute, because this lambda is the charge density, and this current I here can be viewed as charge density times velocity v. And if you really divided B and E together, what did you get? Yeah, the answer is really, really cute. I do hope that you also find that really interesting. And once you find that, you wouldn't be surprised that that's why that sometimes there are some people saying that magnetic field is a relativistic correction of the electric field. That means the magnetic field that I write down here is really just a correction term of the electric field in special relativities. And I think this is not really a puzzle. This is just something cute that you can try out for fun. Okay? And so I guess that's pretty much what I want to say today. And I know there's no more delays. So since I don't receive any question at this point, so I would just end our YouTube live today. And I do hope that you pick up this very interesting and fun stuff about the Green Theorem and trying to really connect the fundamental theorems from 1 dimension, 2 dimension to 3 dimension. We'll talk about more about the 3-dimensional version, the Stokes theorem. So don't worry, Stokes theorem is famous, so we won't miss that. But I also encourage you to read just some biographies on George Green and think about a person, a mathematician. He's a mathematician. He only entered school for 1 year during the age 8 or 9. And he educated himself and learned and developed so many mathematical tools. Okay. So we are learning these beautiful mathematics from a brilliant mind who only attends school for 1 year. And please keep in mind, in George's era, there's no online courses like Coursera, edX, Udacity, and so on. So how can one really try to educate himself through all these difficult mathematics and then come up with these beautiful results? I find that stories and the outcomes really, really, really charming. And I do hope that you would also enjoy all these theorems and the beautiful potential theories he wrote down almost 200 years ago. So I will basically just end the course today. Okay, see you next time.